We're going to spend the next 3 lectures talking about rotational dynamics and rotations. Now, up to this point, we've talked primarily about what we can call translational motion. So here we have a ruler or something, and in this picture, it's just moving translationally or linearly. And so the object as a whole moves along a trajectory, but it does not rotate. We've talked about rotational motion a little bit, but objects, of course, are allowed to rotate. And we haven't dealt too much with this, and so we're starting to now. And then what we can have is the combination of both of those. And so here it's a ruler that's moving along some parabolic trajectory, but it's also rotating. We want to be able to account for both of these types of motion. A really important concept will be the axis of rotation, which is the line things rotate about. And basically everything we talked about would be in definition to the axis of rotation. So here's, it's sort of a simple idea, but it can be tricky in practice, and so I just want to go over it. So here's a gray disk rotating, and this yellow dotted line is the axis of rotation. We can view it here, where it's basically head on. The disk looks really skinny, and this looks like a little line, a yellow dotted line. We can also look at sort of a bird's eye view here, where the axis is just a little dot. Okay, so you got to be careful. But all of our definitions will deal with the axis of rotation. Now, when dealing with a rotating object, our old-fashioned variables come up short. And our old-fashioned variables would be position, velocity, linear velocity, and linear acceleration. And why do they come up short? Well, suppose we have these 5 blue dots, and this little green disk here is rotating about its axis of rotation. When we do this, all these dots are going to go a different distance, right? This inner one goes a much shorter distance than the one that's a little bit further out, and they're all going to have different speeds and accelerations, linear speeds and acceleration. So our old-fashioned values are going to be different for all 5 of these points. And so what we did is we created a new angular rotational value, okay? And basically what that means is all these points are going to go through the same angle, the same amount of radians in the same amount of time. They're going to do the same number of revolutions in the same amount of time. And so we define the angular displacement, all right, which is usually measured in radians. And basically, you know, if I was to draw these points again, so 2 points here and here, as we travel here, they travel different linear distances, but they'll travel the same amount of radians, the same angular distance. And real careful here that it's always positive if counterclockwise and negative if clockwise is our definition. And the whole point is that all points have the same angular displacement. And further, we defined the angular velocity, which is the analog to the linear velocity, and the angular acceleration, which is the analog to the linear acceleration. They all have units that now, instead of involving meters, involve radians. And the really important point is that all points on some rotating rigid body is just a really fancy way of just saying an object that its shape cannot change, are going to have the same angular velocity and the same angular acceleration. That's why we're going through all this business, is to make our lives easier, even though at first it may seem like it's making things more complicated. And what we did with this then, so again, we're going to find that for basically everything we've dealt with before in physics, so here x, v, and a, we now have a rotational analog, and we're going to find that this is going to continue. And we did this a couple weeks back, where we took the linear equations of kinematics and put them into rotational form. So they have the same shape as the equations we've been using. They look like they're in kind of like a different language now. So real quick, just a little refresher here. And so here we have a fan blade that's rotating in the clockwise direction. We want to know is what are the signs of omega and alpha, and assume the fan blade is speeding up. What do you think? All right, hopefully you got that they're both negative. So clockwise is the negative direction, and so since it's rotating clockwise, then this will be negative. And it says that it's speeding up, which means the acceleration will be in the same direction as the angular velocity, and so that'll be negative as well. Just a little tiny bit of a refresher there. So now we'll move on to some new stuff, rotational kinetic energy. So we've talked about kinetic energy. It's energy of motion, and our equation is 1/2 mv squared. All right, now I'll just write it here a little bigger. Now we know when an object is rotating, it also has motion. Therefore, we expect to have kinetic energy rotationally as well. And so to define that, let's look here. And so we'll start out here with a little picture of a blue ball orbiting this yellow ball with a speed v. So it's kind of like Earth going around the sun, maybe. We know its kinetic energy, if it's got a speed v, is 1/2 mv squared. So we can think about this velocity as being linear. What we can also start to do is convert this into rotations. Think about it as rotating. And the way we'll do that is to use the viewer equation. All right, so if I define r as to be the distance from the sun to the earth here, then the linear velocity can be compared to the angular velocity through the radius r. And so we can take that, and if we plug that in to our kinetic energy equation, we get this here. And if I move it around a little bit, okay, I've got a little shape here where I've got 1/2. All right, now I'm going to call this business inside here I. We'll talk about that later. And then omega squared. So you see that now this has a very similar shape to our old equation, 1/2 mv squared, where it's 1/2 some sort of business here, and then the angular velocity squared, where it used to be the linear velocity squared. All right, we're going to call this I the moment of inertia, and so this is the moment of inertia for a point mass, and a point mass is just some object where essentially its mass is, you can essentially think about its mass as being just at one little point. That's what the definition means. We'll talk more about the moment of inertia later. And so our new equation is 1/2 I omega squared. This is the rotational kinetic energy for an object, and it's true for any rotating object. And so now we can think about an object that's moving translationally, like this baseball with a V, and rotationally with an omega. It now has a total kinetic energy where there's two pieces, the translational piece and the rotational piece. Now we're going to find that for almost everything we did before, we're going to have a new rotational version of it, and it's going to be the same kind of picture where the letters will be sort of transcribed almost like it's in a new language. But with rotations, everything's just going to be a little bit more complicated. And so the first piece that's complicated is this I. So let's talk about the I. We call this the moment of inertia. I like to think about this as the rotational version of mass. And it's how much, the technical version is it's how much an object resists an angular acceleration. And so here we have two little objects. They both have the same amount of mass, but the mass is distributed differently. And so in this picture, the idea is that they're rotating about this little dotted line is the axis of rotation. The moment of inertia depends not just on the mass, but on the location of the axis and the distribution of the mass. And in general, mass further from the axis is harder to rotate. And the best example to think about that is an ice skater in the Olympics. Okay, when an ice skater has their arms outward, all right, they're harder to rotate the person, and so they'll generally go slower. When they bring their arms in, okay, when the mass is closer to the axis, they'll speed up. And so that's a nice example to think about that. Here's a picture from the book. So in the book here, you have two wheels, and it's sort of the idea here is that the shaded parts of the wheels are much more massive, so they're really heavy, like maybe this part is some sort of styrofoam or something. And so here the mass is concentrated at the center, here it's concentrated on the rim. All right, and basically it's easier to spin the case where it's concentrated at the center, just like the ice skater. When the arms are in, it's easier to spin. When the arms are out, it's harder to spin. That's the general idea of moment of inertia. Now, let's define how to actually calculate it. So there's two cases. The first case will be what we call a point mass, and we'll show some definitions of how to do this. A point mass, just like that little picture of the Earth, is an object that is so small compared with its distance from the axis that we can forget about its size and consider that all of its mass is acting at one point. And our equation there is going to be this mr squared, and that r is defined as the distance measured from the axis of rotation, and the sigma is just there in case you have more than one object. And the second case, which again we'll talk about, is more common objects, and basically in your book there's a definition, so someone's already calculated the moment of inertia for some common objects, and so we'll show that picture too. And so here's an example of two dumbbells with this one here's got a mass m on both sides, this one's got a mass divided by 2 on both sides, and what we're going to do is we're going to spin these dumbbells around their center, so the axis of rotation is around the center. I want to know is which one has a larger moment of inertia. So give this one a try and see what you think. Okay, hopefully you got B. And so what this would be is we can think about both of these as being point masses. And so if I look at A, I'm going to add up mr squared for two pieces. And so it's going to be m times the distance squared plus m times the distance squared. Now, the distance, again, is measured from the axis of rotation out to your point. And so this would be r divided by 2, r divided by 2. And so when we calculate this, now since it's the same piece being added twice, I'll just do 2 times m r divided by 2 squared. And when I'm all done with that, I get 2 m r squared divided by 4, or altogether 1/2 m r squared. Now for B, it's a similar idea, but now this is m divided by 2 for each piece, and then it's going to be the distance here is going to be just r, since we've made the whole distance 2r. So it's m over 2 r squared plus m over 2 r squared, and so this is going to equal just m r squared. And so another way to think about this is that moment of inertia generally goes like m times length squared. And so here you doubled the length and took the mass in by half in this second case, but since it's length squared, the doubling of the length is in a sense more important. And so that's why you can think about it too that way it comes up bigger. So the length is more important than the mass difference. Now, the second case is more common objects, and what people have done is they've integrated. When you're integrating a more common object, what you do is you break that object into like a little tiny bunch of point masses. So here's 3 little points that are basically the same distance from the center here, okay, which would be just the radius r, and what you do is you add them up like point masses, mr squared. When you do a whole bunch of them, you get what the total moment of inertia is. So this is the moment of inertia for a hoop is mr squared. And so here's a copy of your picture on page 318. It's a bunch of common shapes. So here's like a thin rod about the center, thin rod about the end, a solid cylinder. So here's a cylindrical hoop, which is what we just were talking about, which is mr squared. So you'll see all of these have the basic flavor of mass times distance squared and then times some kind of a fraction. So for a more common object, you can just look it up in the book or on Google or something and find what it has to be. Now, moving on from moment of inertia, we want to talk about forces. So we've seen that F equals ma. When there's a force, it's going to cause an acceleration. So we can imagine the same thing is true for rotations. If I apply a force to an object that's rotating, I can lead to it having an angular acceleration. So we want to talk about forces in a rotational language. And so let's look at an example. So here's a door, all right? And so here's the hinge of the door, which is also the axis of rotation. And so suppose I'm on one end and pushing against, say, a much stronger classmate. Okay, now in this case, if we're pushing on the total end of the door, since the classmate's stronger, they're going to win and the door is probably going to rotate in towards me. All right, now what we can also do, though, is then take that and have the classmate push somewhere halfway in between. And you can try this with your friends. Okay, so even though the classmate is stronger, if I have them pushing on an inside part of the door, okay, that's closer to the axis than where I'm at, all right, I can actually win this time, okay, and be able to push them that way. And this is an example of what's called torque. And so the rotational force depends on where it acts, not only how strong it's acting as. And so further from the axis of rotation, the stronger your rotational force will be. And our rotational force is what's called torque. And so you look at these two pictures here. In this case, we're the same distance from the axis, and so since the classmate's stronger than me, they win. But here, okay, since they're closer to the axis, I can actually overpower them. This is called torque. So force is a push or a pull, a torque is a twist. And our general definition of torque is going to be the cross product of the force and the radius. But we're going to break this down in a lot of cases. And one case you want to really be careful of, because it's the simplest case and it happens very often, okay, is that the simple case where all of the force tends to rotate the object. So here, if this is the hinge of the door again over here, and you're pushing with some force and all of your force tends to rotate the object, okay, then what your torque is going to come out to be is the magnitude of your torque is just going to be that force times that R, okay? And this is again for the case where the force makes a right angle to your distance R. And so in this case, maybe if the force was 10 newtons and that distance was 2 meters, it would be 20 newton meters. So torque is going to have units of newton meters. Now, one thing that can be tricky is how positive and negative torque work. It works just the same way as our direction did for angular accelerations and stuff. And so counterclockwise is a positive rotation. All right, so here if I have, say if I'm balancing something on my finger, as in this picture here, okay, if the thing rotates counterclockwise, it's positive rotation, and so for instance, if my force F2 there is pushing down the other side of my finger, that's making a positive rotation, okay? Now F1, if it's pushing this way, that's going to make this thing want to rotate the other way, and so that's going to be a negative rotation. And so in this picture, F1 wants to rotate it negative, F2 wants to rotate it positive, and so they're actually, though, they're both pointing in the negative Y direction. So you got to be super careful about which way it's actually rotating your object, not which way it's pointing. So torque can be complicated that way. Now, if there's a door in this hinge example, so to open the door, we must rotate about the hinge. So it makes a difference where we push and how much we push. All right, so further on the axis, the easier it is to open the door. We talked about this before. This force is going to be more effective at opening the door. Also, it depends on how we apply the force. If you push here like this, you're just going to push the door into its hinge. You're not going to be able to rotate it. Okay, and so it depends on where you're pushing and how you're pushing. And so let's just look at a quick example. So let's suppose that, so this is a really big door, obviously, that you're pushing, the distance here is 15 meters, and you're pushing with a force of 20 newtons at an angle of 35 degrees. I want to know is how much torque do you think you're applying? Okay, hopefully in this case you got that it was 172 newton meters. And so sometimes only part of force causes a torque. And so here, if we take our force, we can do the y component and the x component. Only the y component will cause a torque. The x component will just push into the hinge and essentially be wasted. All right, and so what we do is our torque is now going to be the y component times our distance r. And so in our case there, to figure that out, you find the y component times the r. So again, for this one here, our force in the y direction would be right here, and so our torque would be the force in the y direction times that distance r, and the force in the y direction would be the 20 newtons, and so this is the angle 35, which would be the same angle as over here. The Fy is the one opposite of that, and so it would be using sine, so it would be 20 newtons times sine of 35 times the 15 meters, and that comes out to be the 172. So now a more general definition of torque, we're going to use what's called the moment arm. Okay, and this one is a little bit less physical, but it can usually be quicker in getting the actual answer. And so torque, it can be defined as the force times d, where d is the moment arm, and the moment arm basically accounts for where and at what direction you apply a force. All three forces here will cause a different torque in this little picture here with the wrench. And so let's look at how to find this. And so here I have a wrench that's 2 meters long, so again it's a really huge wrench, I guess, and you're applying a force of 30 newtons at an angle of 30 degrees. So to find the moment arm, what you do is you define the line of action, which is basically just a line that goes all the way through this force here. The line of action, Just draw a line through the force, and then what you do is you connect the axis of rotation. So here it's this wrench, and you're trying to connect the axis of rotation, that little red dot, with your line of action, the shortest distance possible. And that's, by definition, they're called the moment arm. And it's also going to be always at a 90-degree angle. So when you do that, you're always going to have a nice little right triangle. And so this blue line is the moment arm. And so the torque is the force times the moment arm. So here it's 30 newtons times 2 meters times sine of 30. And so the torque for this particular force would be 30 newton meters. So we'll do some more examples of this in class. But this is how the moment arm works. And what you're doing here is you're finding the length that is perpendicular to the force. Now, just one thing is, the moment arm can be helpful. You're going to use it a lot, but just be real careful about the real simple case. Okay, the simple case where the force is actually at 90 degrees to the distance to the axis. Okay, that'll happen a lot, and that's a real simple case where the torque then is just the force times the distance. You don't want to forget the forest for the trees. So here we got 4 forces with the same strength. Which force will be the most effective in opening the door? Give this one a try. All right, and hopefully you've got that this one would be F1. So we talked F2 doesn't do anything at all, and then here F4 is closer to the axis, and so it's not going to be any good. And here F3 and F1 do act at the same point, but this is at an angle, and so part of your force is wasted. Okay, and so it'll be F1.